In this lecture, we'll start Chapter 11 in Griffith's book on Electrodynamics, the 4th edition. And Chapter 11 is all about radiation. So as we've been working our way through the book, we've been working up to this point where we can now measure or discuss more quantitatively radiation. So we started with Maxwell's equations and using Maxwell's third and fourth equations, or Faraday's law and the Ampere-Maxwell equations. And we were able to show that oscillating electric and magnetic fields produces a wave. Then in chapter 10, we found that if you calculate the potentials, the electric and magnetic potentials you would get for a moving charge, that moving charge would in fact produce a term which we're going to call the radiation field. That if you have an accelerating electric charge produces radiation. So now we're going to study that in greater detail. So the idea is, what we can start with is to talk about maybe the power. So what we have is we have this field radiating outward, and the power, which is just the intensity of through an area, is essentially the integral of the pointing vector through that area. Or I could write it out as 1 over mu naught, the integral of the electric field times the magnetic field captured by the area. So if I have a point here, some source, which is now radiating out, so my power that I measure is the intensity through this area that I'm encapsulating it with. Okay. So since the energy in the electromagnetic wave travels at the speed of light, then I could write down basically the time, t0 is equal to the current time minus basically the time it took to travel from the source to my detector. So basically, so t0 is like the initial time of when the energy left the source, and so the power in the radiation at its initial time is essentially saying, let's take the limit as r goes to infinity of the power at measured at some distance and measured at my current time right here. Okay, so we're going to deal with this process of the electromagnetic waves leaving the source, traveling at the speed of light, and eventually making it into my detector. So now what I want to do is to kind of go over a couple cases to kind of get us started on calculating the radiation fields. Okay, so first we're going to start with electric dipole radiation. Okay, so this is a pretty simple case. Let's say I start with a positive charge Q on this conducting metallic sphere. I start with the opposite charge but equal magnitude minus capital Q, and then they're connected by a thin conducting wire. And what I'm going to do is I'm going to drive these charges back and forth at a frequency omega. So essentially what I'm going to do is I'm going to take the charges And I'm going to take the positive charges and move them this way. And then I'm going to take the negative charges and move them this way. And so what you end up with is cases where you essentially have positive charge here, negative charge here, equal amounts, so 0 charge, and then we have negative charge over here, positive charge over here, 0 charge, and so forth and so on. So I'm going to oscillate these charges back and forth between the two. In doing so, the charges have to slow down, stop, turn around, and go back. So there is going to be some acceleration and deceleration involved in this as it oscillates back and forth between either sides of this dipole. So in that process, these charges should be radiating, they should be producing light, and they should oscillate back and forth. So this is our toy model that we're going to start with. Oh, I should probably label some of the quantities. So let's say the distance between these two charges is d. Okay. So therefore, the charge on any sphere at a given moment in time, let's say the left sphere, would be Q is equal to the initial charge times the cosine of my driving frequency that I move it back and forth. So if that's the charge on, say, the left sphere, then the oscillating dipole moment, the oscillating dipole moment, is P as a function of time, the initial dipole moment, P, cosine omega t, let's say it's in the z direction. So let's say my dipole is pointing now, let's define that as the z direction. Okay, so my initial dipole moment is the initial charge times the distance d. Okay, so now what we have is this dipole moment, which is oscillating back and forth. So, on one hand it's pointing this way, and then it oscillates and points the other way, and then it oscillates and points back the other way. And now what we can do is to write down the retarded potential. So basically the potential at my initial time. And so this potential at some time t is equal to 1 over 4 pi epsilon naught q 0 cosine omega t minus the time it takes for the information to travel divided by the distance, and I'll define what r plus sign means in a minute, minus q0 cosine omega t minus r minus divided by c divided by r minus, where r plus and minus is equal to r squared plus d over 2 quantity squared minus plus rd cosine theta. Okay, which essentially looks like the law of cosines, because it is. So what is this scenario? So let me redraw my dipole. So here is a point in space where I'm going to be measuring my electric potential. And now the distance from the origin to the electric potential is r. The distance from the positive charge is r plus, and the distance from the negative charge is this distance r minus. And the distance between the two, or I should say the distance between the charge and the origin, is d over 2. like so. Okay, so that's the picture that we're working with. And the angle theta is this angle here. So it's the angle between the direction r, origin to the point in space, and the z-axis. Okay, so now what we're going to do is we're going to assume that the separation between the charges is much, much smaller than the distance that are away from it. So we're kind of thinking of this as like a very, very small dipole. And if that's the case, then we can do an expansion of that square root. So we can do a binomial expansion, and r plus or minus is going to be r1 minus plus d over 2r cosine theta. Okay. However, what we want to expand actually is 1 over. So 1 over r plus or minus, it'd really be r squared plus d over 2 squared minus plus r d cosine theta to the minus 1/2 power. And so if we do that expansion, that would be approximately r squared minus plus r d cosine theta to the minus 1/2 power, because d is much, much smaller than r. So we can get rid of that middle term. Now we apply a binomial expansion, and what we get is 1 over r, 1 plus or minus, because we have the minus 1/2 in the exponent, d over 2r cosine theta. Okay, so we basically now have expanded out our distances. So we now have an approximation for r plus and minus, and we have an approximation for 1 over r plus and minus. Okay, so now what we can do is what we can do now is to take a look at the cosine, because what we have is a cosine of omega times t minus r plus or minus over c. Okay, so now we also have to deal with that cosine. Okay, so I think I'm going to stop the lecture right here because this is going to go on a little further. And so in the next video, I will pick up where we left off in terms of taking care of the cosine function, and then what we can do is we can put that into our equation for the potential.